Hello everyone. In this video, we will talk about finding volume of a solid of revolutions, and we are going to concentrate on the cylindrical shell method. For the cylindrical shell method, we are going to concentrate on finding the sum of the infinite shells. Unlike the method of disk, we are going to find the sum of infinite disks. But in this case, we are going to concentrate on the sum of infinite shelves. So the steps are given here for us, and I'm going to go over the step with everyone. Sketch the area bounded by the given function. So in finding the volume, the area bounded by the given function is very important, and we have to shade it, the area, and we also have to figure out what area that we are working with in terms of our given functions. And then we'll be given the axis of rotation, and this axis of rotation will determine the variable of our integration. So in this case, I'm talking about dx or dy. Alright? Okay, so the next step is very important here. Okay, so we are going to sketch the element, okay, associated with the area that we are finding, and then based on the axis of rotation, you are going to get the element that is parallel to the axis of rotation. Unlike the disk method that we have done in previous unit, we are going to identify the vertical or the horizontal element when it's perpendicular to the axis of rotation, but the shell is a complete opposite. Using shell, you must have the elements that is parallel to the axis of rotation. So let me go back to our previous lesson and review a little bit. Okay, so it will clarify our shell method. So right here, what I have is in previous lesson, we are talking about the disk method. Okay, so in this disk method, again, I was asking everyone to pay attention to the axis of the rotation, and then from the axis of rotation, you are going to draw the elements that are perpendicular to this axis of rotation. Okay, so from this you can pull the formula that you need to use. So from here, because of the dx, you know that you are going to choose the formula in terms of dx. Okay, so let's go back to our lesson. So our lesson said this. If we are going to use the shell method, okay, if we are going to use the shell method, then what you have to do in this case is you are going to take a look at what axis of the rotation is given to you. Excuse me, I'm sorry. So let's say I have the axis of rotation is the x-axis. So that means I'm going to draw it right here for everyone. Alright? Okay. So this is the x-axis. And I draw the rotation around this one. And if I have to use the cylindrical shell method, I must draw the element that is parallel to the axis of rotation. So in this case, if I draw the y-axis here, then my element has to be parallel to the axis of rotation. So now you see that you are using the horizontal element. So in this case, you are working with dy. So with dy, you are going to work with these formulas. Alright? Okay. Then, let's move on to the next one. When we have the axis of rotation is the y-axis, and I will explain to everyone why we have the circumference here, why we have the height, and why we have the thickness. Alright, so let's get it clear with the step to find the volume of a solid of revolution, where they ask us to use the shell method, and also they give us the axis of rotation. So for these formulas, the axis of the rotation is y-axis. So I'm going to draw the x and y axis here. So this is my y and this is x. The axis of rotation is this one. Okay, the y-axis. So I must draw the element that is parallel to this y-axis. So if I draw that, it will be this. parallel to the axis of rotation, and this one is my dy. Okay, so let's make sure that we make a note here. All right, okay. So now I will say dy parallel to the x-axis, okay, which is the axis of rotation. So here I will have dy parallel to the y-axis, which is the axis of rotation. So this element is very important. How do we get this element? It's because we follow the step that it has to be parallel to the axis of rotation. Okay, and then we evaluate the boundary of the solid. We set up the definite integral to integrate. So the rest is simple. We just want to make sure that we get the step correct in this case. Okay, before I get into explaining to everyone why we have this formulas, I would like to go to our formula sheet. Okay, so let's go to our formula sheet. I kind of prepared this formula sheet for everyone, and in previous lesson I also showed this sheet as well, and we just talk about the this method. All right, so this is the this method, but in this lesson we are going to talk about the shell method. So each of them have two formulas for you to choose to work with. And which one do you choose? You have to choose the one that associates with the element that you are using. So if you use the horizontal element, then you have to work with these formulas because horizontal element is dy. If you use the vertical element, which is dx, then you have to work with these formulas. All right, okay, so and how do you get dy dx? Because for the shell method it's parallel. Okay, so I'm going to make a little symbol above this formula. This is the shell, so it's parallel. This is perpendicular. Okay, because there are three methods that we will work in this unit. Then we have the disk, the shell, and the washer method, and we need to distinguish which one we are going to use. So it's actually pretty simple because I will ask you what method to use. So I will ask you to either use this method or shell's method. And then we just have to follow the rule with this method. Concentrate on the horizontal or vertical elements that you are going to use, right? So, and the factors that determine your element is the axis of rotation. Okay, so keep remember that this is perpendicular, shell is parallel. Alright, so let's get back to our lesson. Okay, and I am going to explain the formulas for everyone. So we are talking about the cylindrical shell method, right? So that means we must have infinite number of shells, and we add them all up. That means we will have to take the sum of all of the shell, and because of the variety of the shape that we have to work with. Excuse me. Sorry, I just want to drink a bit of tea. Okay, so if we are talking about the cylindrical shell method, then we need to talk about the sum of infinite shells. And because of the shape that we are working with, it's not like a cylinder or a shape that we have formulas to work with. We have varieties of shapes. Therefore, we need to work with the functions, right? So, and since we are working with the area bounded by the function, and we revolve that area about the axis of rotation, we need to apply integration. Okay, so now you realize that calculus is actually very powerful in terms of the application. If I want to find volume of a certain shape, I have to apply calculus with the integration and then the fundamental theorem in order to calculate its volume. So in this case, I am going to show everyone a document. Okay, so this is more like to demonstrate to everyone the method of shells, or the cylindrical shell method, is the same thing. Okay, so this is the sum of infinite shells, and I want to show everyone how we have the sum of all of this shell to form the shape, and why we come up with the formulas. Okay, so first of all, take a look at this diagram on this side. So let's say I have this area here that I shaded for everyone in yellow, and I have to revolve this area about the y-axis. So I show the arrow here. I'm going to revolve this area about the y-axis. Then, if I have to use a method of shell, it means that I need to draw the element that is parallel to the y-axis. Okay, so in this case, my element is the vertical elements right here. So it has to be the dx, right? Vertical elements is always dx. So I write dx here for everyone to see. Then I am going to take this single shell that I have. So that means this element is part of the shell and is revolved around the y-axis. Project it, the mirror image on the other side, and revolve over to the other side. So I have a shell, okay? So if I have this shell, then I'm going to stretch it out. Okay, I'm stretch it out for everyone to see that I actually have this shape. How do I find the volume of this shape? Okay, so that means I am going to take this length from here to here, okay? And I have to multiply with the thickness, which is dx, and I have to multiply by the function fx. So now you see right here to here is my function fx. Here is my thickness of my shell, and this is the length, which is equal to the circumference. Okay, so if we revolve this about the y-axis, we are going to form a circle. So that means this length from this point to this point will be the circumference of this circle. So what is the circumference? What is the formulas for that? Is 2 pi r. Is that right? Okay, so 2 pi r. But what is r in this case? That means it's x. So that means I'm talking about this point to this point is whatever value that I have here for the x. Okay, so for me to find the sum of the infinite cylindrical shell, I have to do this. I need to take the integral from x equal to a, from x equal to b, and I have to, and what is the volume for this, right? So the volume is 2 pi x times the xx times the thickness, which is the dx, but I need to find the volume of all of this infinite shell. Depends on the function fx right here, so I have to use integration. So the formula is 2 pi x times fx times dx is the volume of one cylindrical shell itself. But I have to find the infinite of this shell, so I have to apply the integral. Okay, so my function fx is right here. Here's my function fx. Okay, so to do that, I have to take the integral of the entire function in terms of dx. Because I'm working with dx, my upper and my lower limit has to be a and b from where the value is actually on the x-axis. Alright, so let me fill in here. This is my x-axis. It's kind of get cut off because of the figure somehow got cut off. Okay, so now you see where the 2 pi coming from. Then according to the properties of integration, I can bring the constant across the integral sign. So 2 is a constant, pi is also a fixed number, so I can bring 2 pi across the integral sign. So in the end, my formulas become like this. Volume equal to 2 pi times the definite integral. A is lower limit, b is upper limit. The x, okay, multiply the function fx times dx. So what is the function fx in this case? The function fx is actually y equal to, okay, so in this case, this is actually equal to y. Okay, that means you have to solve for y. Okay, so keep that in mind. So vice versa here, right? So if I have a shape and I revolve it around the x-axis, then my thickness, which is the horizontal element, so it will be dy, and then the circumference will be 2 pi times y and times dy, and this function now is become f of y. Okay, so the function with respect to y. Again, I bring the 2 pi across the integral sign, and you know that the upper and the lower limit will have to be associated with the y-axis because we are working with the dy in this case. And what is f of y? Okay, so keep in mind fy will be equal to x. Okay, so this is fx is equal to y, and fy is equal to x. That means we need to solve for x. So I hope that you know where the 2 pi coming from, because we are talking about circumference in this case. All right. Okay. So let's get back to our lesson, and we will work with example. Okay. So we work with example. So now I'm going to fill in here. Again, I just want to make sure that I have this on this page as well. So fy will be equal to x. That means you need to solve for x. Okay, you isolate the x. So this fx will be equal to y. That means you need to solve for y. Okay, so let's work with an example. Okay, so this example said that I'm going to use the shell method, find the volume of a solid generated by the area bounded by the given curves. Okay, even though it's a straight line, I just have to put it as the general term of the curve, because honestly, a straight line in calculus, they actually a curve in terms of the tiny point connected together to make a function. So even though I put a curve, which is a straight line, is represent the same thing in mathematical terms. All right. Okay. So first of all, we are having y equal to square root of x minus 3, and you know that square root of a function, it means that you are having a parabola opens to the side. So I'm going to highlight that for everyone. So if I highlight this, let's use blue. So this is my parabola open to the side, and it's right here. Okay. So this one should be my y equal to the square root of x minus 3. Okay, so first of all, they said I'm going to use the shell method. So I'm going to make a note for myself that I need to find the element that is parallel to the axis of rotation. Okay, so the symbol for parallel, if you want to be okay, so it will be like this. So that is parallel symbol. Okay, so it's parallel. Then the axis of rotation is the x-axis right here. Okay, so I'm going to have a horizontal element. Okay, the horizontal element, and in this case, I will work with dy. So, but let's find the area first. So the area set y equal to 1. So that must be this line right here, y equal to 1. Okay, now y equal to 2 is this one. So y equal to 2. Okay, so, and then x equal to 0. X equal to 0 is the y-axis. So it's actually this one right here. Okay, so let's shade it our area. Okay, we shaded the area. And now the axis of rotation is the x-axis. So I'm going to draw my element. So horizontal element. So this one is parallel to the axis of rotation because I have to use the shell method. Okay, so after this point, we are good to go, right? Because we are going to take this area and we revolve it about the x-axis in this case. And we are going to find the formulas that we need to use for this. Okay, so if we find the formulas, it's up here. We are having the horizontal element, so I'm going to use the formula with the dy. So the formulas I need to use is v equal to 2 pi, the integral from c to d, because I'm working with dy, so I would take y times x times dy. Okay, don't forget x is actually f of y. This y is the value that you need to put in here, is the variable that is need to remain as the integrand, but the x is the one that you are going to derive from the given function. So which is this one? The given function you are having right here is this y equal to the square root of x minus 3. Because if you revolve this area around this, so this is very important here. Okay, so then now I am going to get the y equal to the square root of x minus 3, and I'm going to solve for x. Okay, so I'm going to solve for x. That means I am going to square both sides. So this is a half. Okay, I square this. So that means y squared will be equal to x minus 3. So we explained this concept in previous lesson. Now I'm going to take y squared plus 3 so I can have x isolated. So now this x is isolated. This value for x is you need to substitute that in here. So in this case is a function, right? So now your formulas for the v will be equal to 2 pi, okay, from c to d of y multiplied by y squared plus 3 dy. Okay, so now what is c and d? C and d is actually the two values that are given to me, 1 and 2. So I might as well fill that in. Okay, so this here is 1 and 2. So let's integrate this. Okay, integrate this. What I am going to do is I'm going to multiply this inside a bracket. Okay, so we have v equal to 2 pi integral from 1 to 2 of y to the exponent 3 plus 3y and then dy. So what is the integral of this one? Okay, the integral of this will be v will be equal to 2 pi and integral of y to the exponent 3 is 1 over 4 times y to the exponent 4. Integral of 3y is 3 over 2 times y squared. Evaluate from 1 to 2, apply the fundamental theorem. So now it should be 2 pi, and I must multiply this with f of 2, subtract the f of 1. Apply fundamental theorem. Okay, so I will be having the solution like this. So v equal to 2 pi, okay, and for f2, I will have it as 1 over 4, where the y is substituted with the 2. Okay, so where the y is substitute with the 2. So I have 2 squared in this case. So that times that times that. Now I'm going to, I can write it as well if you want me to put a bracket around it. Now I subtract this with where the y is. Now it will become a 1. Okay, plus 3 over 2, 1 square, close the bracket. Close the brick bracket as well because everything will have to multiply by 2 pi. So here I would like to show everyone that this is my f of 2 and this is my f of 1, and I double check that, and v will be equal to 2 pi. Okay, so 2 to the exponent 4 is 16 divided by 4 should be 4. And in this case, I should have 6. Okay, so here I should have a 1 over 4 plus 3 over 2. And v will be equal to 2 pi. So this is 10 subtract 7 over 4. Then in the end, the answer is 2 pi times 33 over 4. So I'm going to cancel this with that. So I will have, this is the 2 now. So I will have 33 pi over 2 unit cube. Okay, as we agree that we are going to keep our answer in exact form and that you keep the pi and your answer remain as the fraction in lowest term. Okay, so I have a few minutes left. I'm going to show everyone the shape that we are working with. And I will continue with the next video because we have another example to work with. Okay, so before I do that, I just want to quickly fix this part. So it's 3 over 2. Close that and close the big bracket. Alright. Okay, so let's take a look at the shape that we are working with. So the shape that we are working with is in fact this one right here. Okay, so let's analyze this. Okay, I'm going to draw the axis through this. So drawing the axis through this. So this is my y-axis there. So this will be my x-axis. Okay, I try to be as exact as possible, but I don't think I have the exact in the middle here, so I'm going to try to stay right in the middle of this. Okay, but I need to have a straight line. Yeah, pretty good. No, I think I better do it again. Okay, so when you are getting old, like I'm getting old so I can't see very well. Okay, now so here is my y, here is the x. Okay, here is my parabola, and here's y equal to 1, y equal to 2, and here's this x equal to 0, and this is the area that we are working with. Okay, and then at the same time you see that I'm having the element, right? So the element is okay. All right, you see, and we are going to revolve this about the x-axis. So in this case, so if you revolve it around the x-axis, you are going to make this shape. Okay, you are going to make this shape right here. Okay, so that is the shape upside down. Okay, so I will continue with the next video. Okay, I will continue with the next video because I only have just a few seconds left. Alright, thank you everyone.